There's this force all around us. It can create and destroy, it can heal, and it can harm. It's what powers the sun over our heads and the very earth under our feet. Today, we're going to demystify one of the most powerful and maybe one of the most misunderstood forces in the entire universe: radioactivity. And this whole idea of it being both good and bad, it isn't new. In fact, the very people who discovered it saw this coming. Over 100 years ago, when he was accepting his Nobel Prize, Pierre Curie basically said, hey, this stuff is amazing, but it could also be incredibly dangerous. That tension, that duality, well, that's the story we're exploring today.
So, to really wrap our heads around how this all works, we have to start at the very beginning. We need to go small. I mean, really small, right down into the tiny, unstable heart of the atom itself. Okay, so first things first, an atom's number of protons is like its fingerprint. It's the one thing that tells you exactly what element you're looking at. If it has 6 protons, it's carbon, every single time. If it has 8, it's oxygen. That single number defines its entire identity. But here's where it gets interesting. While that proton number is locked in, the number of neutrons can change. So look here, both of these are carbon atoms, right? They've both got 6 protons. But the one on the right, carbon-14, has a couple of extra neutrons packed in there, and that makes its nucleus, well, unstable. It's kind of like a rebellious cousin, just buzzing with all this extra energy it's dying to get rid of. So what happens when these unstable atoms finally decide to let go of all that pent-up energy? Well, that is where we get radiation. It's almost like an atomic sigh of relief. The atom just throws off its extra baggage, either as tiny, high-speed particles or as powerful waves, and in doing that, it finally gets to calm down and become stable. That burst of energy that gets released, that's what we call radiation. And you should know, not all radiation is created equal. Its real power comes from its ability to knock electrons off of other atoms. It's called ionization. So you've got alpha particles, which are like tiny bulldozers. They're big and clunky, and you can stop them with a simple sheet of paper. Then you have beta particles. Think of them like little bullets. They're smaller, faster, and you'll need something like aluminum foil to stop them. But gamma rays? Whoa. They're like ghosts, just pure energy that can phase through almost anything, which is why you need thick, heavy lead to protect yourself. So we've got this invisible force that can be super helpful, but also super harmful. If you can't see it or feel it, how in the world do you measure it? How do you know how much is too much? We use a special unit called the sieverts. And the best way to think about it is like a sunburn. The amount of sunlight hitting you is just raw energy, but how bad the burn is depends on your skin, right? The sievert is kind of like that. It doesn't just measure the raw energy, it measures the actual biological effect on your body. It gives us a much clearer picture of the actual risk. Okay, let's put this into perspective, because the numbers are what really matters here. A flight across the Atlantic, you get about 30 microsieverts. A chest x-ray, about the same, 30. But now look at that last bar. Just by living your life on planet Earth for 1 year, from stuff in the ground, from the sun, you get around 2,500 microsieverts. So yeah, context is everything. And now, let's look at the other extreme. 4 sieverts. That's 4 million of those little microsieverts we were just looking at. A dose that big, delivered all at once, well, it's lethal for about half the people who get it. That number right there, that's the dark side. It's terrifying, no question. But just like Pierre Curie predicted, that exact same power, when we learn how to control it, can be an incredible force for good. The danger, of course, is burned into our collective memory. From the atomic bombs that ended a world war to the absolute horror of Chernobyl and the disaster at Fukushima, these events show us the terrifying, heartbreaking cost of what happens when things go wrong. When you see devastation like that, it's really easy to think that radiation is just a purely destructive force. But is that the whole picture? Is that the whole story? No way, not even close. And the proof is in amazing technologies like hadron therapy. Okay, think of it like this. It's like a microscopic high-tech water balloon. Doctors can throw a beam of particles that passes right through healthy tissue without doing any damage, and then it bursts with all its energy with pinpoint accuracy, right inside a tumor. It obliterates cancer cells while leaving everything around them almost untouched. It's incredible.
So how do we do it? How do we walk this tightrope between the immense power of the atom and the absolute need to protect ourselves from its risks?
Well, we've actually gotten really, really good at harnessing the atom for good. We split atoms to power entire cities. In medicine, we create these amazing custom isotopes like technetium-99m. It has a super short half-life, which just means it decays and disappears from the body in a few hours. So it's perfect for medical scans. It lights up what doctors need to see, and then poof, it's gone. We even use it to wipe out diseases without using pesticides. The possibilities are just astounding. And the way we manage all that risk, it comes down to a really simple but really powerful idea. ALRA, as low as reasonably achievable. It's basically us admitting that, hey, zero risk isn't possible, not on a planet that's naturally radioactive. But it's a promise to always, always weigh the benefits against the risks, and to never, ever use a single bit of this power more than is absolutely necessary. At the end of the day, the atom is really just a mirror. It reflects our own incredible ability for creation and for destruction. The physics itself doesn't care. It's neutral. So the real question isn't whether we will use this power. The real question is, how will we choose to wield it?